Okay, this is going to be the third video on how to find the interval of convergence of a power series. And if you haven't done it yet, I would watch the first two videos and you'll understand a little bit more about where these rules come from. But just to go through this. Now, when you're trying to find the interval of convergence of a power series, what you're really asking for is this, is for some values of x, the series will converge, and for other values of x, the series will diverge. So you'd like to know in what intervals do you get values of x that makes the series converge. And as we saw in the first two videos, the primary tool for doing this is the ratio test, and we'll use the ratio test to find the radius of convergence. So again, it doesn't hurt to just a quick review of the ratio test so that you'll remember what that is. And hopefully you've had this earlier in your course. So what the ratio test says is that if you have a series with non-zero terms and you find this limit, if the limit is less than 1, then you can show that the series converges. If it's greater than 1, the series diverges, and finally, if it's equal to 1, then the ratio test fails, and you had to use some other test. Now, when you're working with intervals of convergence, we're going to primarily be concerned with this right here. We want to know, where is this limit less than 1? Because where the limit is less than 1, then the series converges. So that's going to be the ratio test. Now, if you need to, again, it's been a while since you've used the ratio test, you might want to review the ratio test videos before you start these interval of convergence videos. But let's go back to our problem. Now, when you've got this, and we're going to work with this problem right here in this example, so we'll move it down just a little bit. And as we discussed in the first two videos, when you use the ratio test and you find this limit, there's really only three possible outcomes. Either that limit is going to be equal to 0, it's going to be equal to infinity, or it's going to be equal to some fixed number. And depending on what you got. So in the first video, we did a problem where the limit was equal to 0. If the limit's equal to 0, then the radius of convergence was infinity, and the series converged for all x. In the second video, we looked at an example where the limit was equal to infinity, which means that the radius of convergence is equal to 0, and the series only converged at the single point x is equal to c. And then in this video, a little heads up here, we'll find one where the limit is equal to some fixed number. So the radius of convergence is equal to some fixed distance, and you can show that the series converges in that interval. Now, in the first two videos, we did this. If the limit was equal to 0, you did step 1 and you were finished. If the limit's equal to infinity, we did step 1, used the ratio test, and we were finished. You didn't have to worry about the endpoints. But in this third case here, if the limit turns out to be a number, we'll actually scoot down. You're going to have to add an extra step, and it looks like this. So if you find a fixed interval of convergence, then you have to remember the ratio test always fails at the endpoints of the interval of convergence, so you must test each endpoint separately using what I'm going to call any appropriate test. So any of the convergence tests that you've had before, you can use to find out what's going on there. So again, if you've got a fixed interval, you have to check the endpoints of the interval to find out whether they should be included or not included in the interval. So with that all in mind, let's go ahead and run through this problem and see what it looks like. And we'll follow the same steps that we've done before. Again, using the ratio test, the denominator is the original series, the numerator is the original series with everything set to an n plus 1. So usually the first thing I'll do is just go ahead and write the original series in the denominator here. So I'll come down, and the original series is x minus 3 raised to the n power divided by n. Then in the numerator, write the same thing, but everywhere you've got an n, change it to an n plus 1. So this would be x minus 3, and in place of n, I'll put an n plus 1, divided by, and then put an n plus 1 right here. Also, before we get started, let me do one last little reminder here too. Notice, this is in the form x minus c. So you know on this one that this series is going to be centered at 3. So x minus c would be equal to 3. So you've got a series that's centered at x is equal to 3. Okay. So we'll go down here, and now it's just a matter of solving this. So this is going to be the limit as n approaches infinity of the absolute value of, and again, we got a fraction divided by a fraction, so we'll invert and multiply. So I'll go across here, and first of all, I'll write the numerator down, which is x minus 3 raised to the n plus 1 power divided by n plus 1, then times, and take the denominator and invert it and multiply it. So we'll change it from a division problem into a multiplication problem. So in the top you'll have n, and then you're going to have an x minus 3 raised to the n power, and then the whole thing is inside absolute values. Now at this point, you can do the following, is write this thing in its expanded form so some things will cancel out. So what I'm going to do is this. I'm going to take this x minus 3 to the n plus 1. I'm going to write it as x minus 3 to the n times x minus 3 to the first power, because that's what this n plus 1 is. So if you spread it out like this, we'll replace this one with these two. And the reason you're doing that is that will allow you to cancel some stuff out. So in this case, here's an x minus 3 to the n power in the bottom, and x minus 3 to the n power in the top. This one will cancel out this one, and it's going to leave you then with this. This would become the limit as n approaches infinity of the absolute value of. Now in the top, the only thing that you've got is x minus 3 times n divided by, and you've got an n plus 1 in the bottom, and you've got the absolute value of that whole thing. So I will let that be, and I'm going to use the same trick that we used before. And again, remember, if you take the limit, the variable in this thing is n. So you can treat the x minus 3 as a constant, and I'm going to bring it outside the absolute value. So the limit of a constant of something is you can bring the constant outside the limit. So I'm going to rewrite this as the limit as n approaches infinity. And the only reason I do this, to me, it makes finding the limit make a little bit more sense. So this will be the absolute value of, I'll leave it as n divided by n plus 1. Here's that absolute value. And then I'm going to take this x minus 3, because I can treat it like a constant. I'm going to bring it outside, which will put it out here. It'll be its own absolute value. So the absolute value of x minus 3. So all I did in that step is just bring the x part of the expression on the outside. Now the reason I do that is because now it makes it a lot easier to evaluate this limit. You only have to look at the n part. So let's do that. Now again, you can think of this as being polynomial on the top and a polynomial on the bottom. They're both to the same power, so you might remember from your limit rules that as you go off to infinity, the limit is just the ratio of the two leading coefficients. So this entire thing will turn into a 1. So the limit, as n goes to infinity, the limit of this expression becomes a 1. But you've still got this absolute value of x minus 3. So at this point now, you have found the limit. The limit is equal to this. Now remember, from the ratio test, what you want to know is where is this limit less than 1? So we'll always check it against and see, is it less than 1? And I like to put a little question mark here just to remind me that's what I'm trying to test. So now the question is this. For what values of x is this thing less than 1? So what you've really got here is this 1, you can just forget about it. It's like having x minus 3 is less than, the absolute value of x minus 3 is less than 1. Now, whenever you have an absolute value less than a number, you can rewrite it as x minus 3 is less than the positive value, but also greater than the negative value of 1. So you can write it like so. Change this absolute value form into this form. Now the next step, you want to solve for x, so go ahead. Since that's a minus 3, I'll add 3 to this term, add 3 to this term, and add 3 to this term. And when I do that, that's going to give me 2 is less than, this will be x, and this is going to become 4. So what this gives me is an interval of convergence. I think I'll draw a picture of it right here. If I drew it, and let's kind of put it on a number line. Sometimes it helps to have just a rough picture of what this thing looks like. So here is the number line. Let's see, it goes from, and I think we'll use black here again. It goes from 2, and it goes over to 4. The center would be at 3. Now in this case, you showed that the radius of convergence goes from here to here and from here to here. So the radius of convergence is 1, and you've now got the interval. So this thing is going to converge everywhere in this interval. But there's still one thing you have left to do, is the ratio test fails at the endpoints, so we'll put a question mark right here, and we'll put a question mark right here. Is when you finish this, there's always less than, but maybe it's less than or equal to. So possibly you include the endpoints, possibly you don't. And to do that, that's where this last step comes in. So you have to test each of these things first. So what happens is the ratio test fails at the endpoint. So to test each one of the endpoints, you take each limit. So the endpoint, the left endpoint's a 2, the right endpoint's a 4. So take a 2 and take a 4 and plug them into the original function and then evaluate that and see what happens. So again, our original function, if we go way back up to the top, the original function was x minus 3 to the n divided by n. So we'll rewrite that back down here. So again, I'm going to test, I'll have, this is going to be for the left endpoint. So left endpoint. And I had the summation from n equals 1 to infinity of x. This would be, remember, it's x minus 3 to the n divided by n. So when you're testing the left endpoint, plug in a 2 for x. So that's going to be the summation from n equals 1 to infinity. And in place of x, put a 2 to the n divided by n. So that gives you the summation from n equals 1 to infinity. And this is going to become minus 1 to the n divided by n. Now at this point, just like the thing says, is since you're working with a fixed number here instead of x, find out whether this series converges using any of the previous tests. And that would be things like the p-test, the alternating series test. Any test that you've used previously, you can use with this one. Now, hopefully you'll recognize this. I like to think of it like this. And you use whatever you think is the easiest test to get that. So I'm going to rewrite this like this, is minus 1 to the n, and I'll think of it times 1 over n. Now, hopefully you'll recognize the 1 over n is just a harmonic series. That's one of the special series that you've done. Now, normally a harmonic series would diverge. But when you put this minus 1 to the n, what you're going to have is an alternating harmonic series. So sometimes it helps if it helps you write out the first few terms. This would give you a minus 1. The next term would be a plus 1/2. The next term would be a minus 1/3. Next term would be a plus 1/4, and so on. And then plus, it goes on forever. So if you recognize this as an alternating harmonic series, you should remember that an alternating harmonic series converges. So from this, you can say that because it's an alternating harmonic series, and an alternating harmonic series converges. So because it converges, that means that you include the left endpoint. So include the left endpoint. So what that means up here on this one is that this is going to be included and this will have an equal sign with it. So that was the test for the left endpoint. Now you have to separately test the right endpoint. So let's do that one. So we'll scoot that down to here, and this time we'll check the right endpoint. So to test the right endpoint, so the right endpoint. Now we use the same thing, summation from n equals 1 to infinity of the original problem, x minus 3 to the n divided by n. That's going to give you the summation from n equals 1 to infinity. And in place of the x, this time, put the right endpoint, which was a 4. So in the first one you plugged in a 2, this time you're going to plug in a 4. So this is going to be 4 minus 3 to the n power divided by n. which is going to give you this summation, n equals 1 to infinity. 4 minus 3 would be 1 to the n power, divided by n. And now, 1 to any power is just 1, so that's going to turn into this summation from n equals 1 to infinity of 1 over n. So now the question is, does this series converge or diverge? And again, what that is, this, you should recognize this. This is not a harmonic series. It's not this one up here was an alternating harmonic series. This is just a regular harmonic series. And you might remember that a regular harmonic series diverges. So you're going to know that this thing is going to diverge, and you have to justify it. So you can justify it by either saying one possibility. You can say it diverges because it's a harmonic series. Or there's other ways to do it. If you wanted to, you could think of this as n to the first power, and you could also justify that it diverges by a p-series test. So if you have a p-series with the exponent equals to 1, then that series diverges. Now what this means, if it diverges, that means that you do not include the endpoint. Include the endpoint. So you do not include the endpoint. So again, when you justify your series, you need to explain why. So sometimes there's one explanation, sometimes there might be more than one. But in this case, in the first one, at the left endpoint, you include the endpoint because it converges. In the right endpoint, you do not include the endpoint. So in the final answer, when you go back up here, and we'll just put it right here. What you showed is that, and I think I'll do them in red here so they kind of stand out. You showed that you include this endpoint, so it's going to change to brackets. So you could either write it like this. You could write the final answer as including the brackets from 2 to 4, and this one would be open. That's one way of writing it. Or you could write it as 2 is less than or equal to x is less than 4, and that would be another way of writing. So either one of these two would be a valid way of writing the interval of convergence. So again, just to remind you is if you go back up here on this third thing, if it turns out to be a fixed number, you use the ratio test, and the ratio test is always going to give you an open interval. So at the end of the ratio test, there will never be an equal to right here. And you have to test each of the endpoints separately to find out whether or not you need to put an equal to, whether or not you include the endpoints. And when you just plug in the number, and as far as justifying it goes, it's just which, and I'll put any appropriate test. So any test that you can use to show that the thing converges or diverges. If that specific series converges, then you include the endpoint. If the series diverges, then you don't include the endpoint. And then your final answer may or may not have an equal to with those greater than or less than. So that's an example of a fixed interval where, in addition to the ratio test, you had to include the endpoints to get the final answer.